Okay, so did you notice the pattern between the location of the vertex, point-wise, and the given equation? Let's summarize what we've learned then. If you can somehow write the given equation in this form, y equals, let's use a times as a constant times the quantity x minus h squared plus k, then what we've discovered with these examples is that if you can write it in this special kind of form, I call it the standard form or vertex form of a quadratic equation. Your book doesn't really have a name for it, but most books call it the standard form. I like calling it the vertex form because when it looks like this, when it's of this form, it turns out that hk is the vertex. hk is the vertex, and a is a constant. A is the same a as before. When you write it out, y equals ax squared plus bx plus c, it's the same a. So that's why we call it vertex form. You can immediately then identify the vertex when it's in this form. Just whatever value you're subtracting from x is h, is the first coordinate of the vertex. Whatever value you're adding to the squaring function on the outside, that's k. So graphically, we know that every quadratic equation with two variables graphs to be a parabola. It will either open up, it'll be a smiley face, or it'll be a frown. Right? Either way, we call this shape is a parabola. And whether or not it's the low point or the high point, that point is called the vertex. So I'm kind of summarizing in pictures a little bit of what we talked about. HK is how we generically label the vertex, first coordinate h, second coordinate k. What determines whether or not it opens up? Did you pick up on that from the examples? What was special about those two parabolas we plotted going down? Y equals negative x squared and y equals negative 2x squared. What was special? The a, the guy in front of the x squared, was negative, so when it opened down. So a is negative if it's a frown. Hey, that's easy to remember. You're feeling negative, you're frowning. Whereas when a is positive, it's a smiley face, right? It's happy, it's positive. For every parabola, this I haven't mentioned yet, for every parabola, there's a vertical line that cuts it in half, right? If I drew a vertical line right through the vertex, wouldn't it cut the parabola in two perfect halves, like mirror image halves of each other? Yeah. So if I draw just kind of a generic parabola here, and I could draw it opening downward too, that wouldn't matter. There's a vertical line that cuts it in half. So we have a name for this vertical line that cuts it in two perfect halves. We call it the axis of symmetry. Basically, a line of symmetry, axis is a fancy word for line. I don't know why it's fancy, but it is. It's a line of symmetry. And anytime you hear about a line of symmetry, all it means is if you graph this on a piece of paper, if you graph the parabola on a piece of paper and folded it across the line, the two halves would touch, right? That's what it means. And you can use the axis of symmetry to plot, if you know the vertex, you can use the axis of symmetry to help you plot a parabola very, very quickly, as you'll see. So what's the equation of the axis of symmetry? What's the equation of any vertical line? If you know, for instance, that the vertex, V for vertex, is HK, the equation, remember, of any vertical line is x equals a constant. Whatever its horizontal position is, it's x equals that constant. And we know what the horizontal position is in terms of the vertex. It's h, right? So the equation of the axis of symmetry, anytime you're asked to find the axis of symmetry, you're asked to find the equation. The equation is x equals h. And then every parabola has a low point and a high point, right? It corresponds with the vertex. But the low value is the y coordinate of the vertex, or the high value, the maximum value, is the second coordinate of the vertex. So k is special as well. K, the second coordinate of the vertex, is always either the maximum value of the function or the minimum value of the function? In this particular case, because it opens up, k is the minimum value. But if you had a parabola opening down, like that, then k would be the maximum value. So you still call the vertex hk. In this case, k would be the max because the parabola is opening down. In other words, if a is less than 0, it's going to have a maximum value, right? Because that means it opens down. It has a high point. If a is greater than 0, that means it's going to have a minimum value because it opens up. And so the vertex corresponds with the minimum, but the actual minimum value of the function is the second coordinate. A lot of students think of it as the entire point, but no, if you're looking at function values, those are output values. The second coordinate would be either the min or the max. Okay, we're almost done, and I'm going to show you how to graph these things. Anytime you meet a new function, you shake its hand and say, hey, what's your domain? So when I say domain of a function, remember, we're talking input values. So there's two ways to write a quadratic function. You can write it in that multiplied out form, ax squared plus bx plus c, f of x equals ax squared plus bx plus c, or you can write it in what I like to call it vertex form. Most books call it standard form. Your book doesn't call it anything. It just calls it this form. A times x minus h quantity squared plus k. You can write it in either form. So I don't need that middle f of x. I'll just write it like that. So either way you look at it, it's going to have the same domain. It's kind of easy to think about in that first form as far as what you're allowed to plug in. So domain values, all the values you're allowed to plug in. And is there any value of x you can't plug in, square, multiply by a, and then add b times that input, and then add c? Is there any number you can't do that to? Any real number? By the way, when we're talking function inputs, we're only talking real numbers. You can plug in negative numbers for x. You can plug in 0. You can plug in positive numbers. You can plug in anything. You can plug in anything. And again, when I say anything, we're talking real numbers here. So what's the domain then? D for domain? Well, it's all real numbers, right? So in interval notation, you could write negative infinity to infinity, negative infinity, comma, infinity. And that means all real numbers, right? That's not true for the range, right? So the domain is not all real numbers for the range. I'm sorry, the range is not all real numbers like the domain is what I meant to say. In fact, what would the range be? You've got two choices. So if it opens up, the vertex is hk. Either way, if it opens up or down, the vertex is hk. So there's two choices. Suppose it opens up. In other words, suppose a is positive. Then how low does it get? How high does it get? That's what you think about when you think about range. How low does it get if it opens up? What's the low value of the function? The minimum value. K. So, and it actually gets to it. So I would use a bracket if I'm using interval notation. So if it opens up, then the range goes from K. Does it keep going up? Yeah, look at the arrows. It keeps going up to infinity. Or, yeah, now that's if a is bigger than 0, right? If it opens up. Or, what's the low value if it opens down? Yeah, well, it never gets there, but that's how we think of it. Negative infinity. And then what's the high value? It has a maximum of k. K is included, so brackets around k. And that's when a is less than 0. I don't think you have to memorize that, guys. If you can graph the parabola, which you're required to be able to do in this class, then you can figure it out just by the range out by just looking at the graph, right? So don't feel like you have to. You should know that you can plug in anything you want, so the domain is all reals. But you can come up with the range based on the vertex and whether or not it opens up or down, of course.